All right, so we're gonna look at how we can solve some real full binomial probability distribution problems. So we can look at problems that'll be like the ones on your AP exam. Now, luckily, there's this good formula and function in your calculator that'll save you the time for not having to do all those tedious calculations. So in your graphing calculator, you're going to see that you have a function called binomial PDF and binomial CDF. So depending on your version, yours may look a little different. I have the most basic, so usually this one requires the most memorization. So you see how we have the normal ones. That's what we were using up to now. But if you scroll down, you'll see binomial PDF, and then here the syntax will be that you're going to enter a number of trials. Let's just say it's 2. P will be the probability. Let's say it's 0.5. K, let's say it's 1 or something. So syntax will be to enter NPK. Make sure you put commas. That's if you want to find the probability that x equals k. Now, if you want to find the probability that x is less than or equal to k, you're going to use binomial CDF. That means binomial cumulative density function, if you're curious. So scroll down back to distribution. And here, NPK, just like usual. So we're going to go through a problem in just a minute there. So then that's going to make it much easier to know how to use it. So in general, I recommend this process and these guidelines for when you're solving these full length problems. Start off by making sure that you specify the distribution that you're dealing with. So specify the binomial distribution with the number of trials n, the probability p, and what you're trying to find, n equals 5 or n equals 10 or like your k value. Make that clear. Then the rest is really to do the calculations. Do the calculations, and if you use a calculator, make sure you mention the syntax and show your work with the calculator, shown. And the last thing, like usual, with statistics, make sure you put your answer in context. Don't just have a number. Make sure you put the number in context of the problem, because that's usually the hard part. And you're going to know what I mean in just a minute. So let's go through practice one. Yeah, I don't want to show the answer yet. All right, let's look at this. Right, last kiss. Do people have a preference for the last thing that they taste? Researchers at the University of Michigan designed a study to find out. The researchers gave 22 students 5 different Hershey's Kisses, milk chocolate, dark chocolate, cream, I guess, caramel, and almond. Oh, Hershey Kisses, not Kisses. Okay. In random order, and asked the students to rate each one. So participants were not told how many kisses they would be tasting. So they didn't know how many they were going to, be going with. They didn't know if it was going to be the last one, or if they had a couple more. However, when they got to the 5th one, which was the final kiss, they were then told that was going to be the last one they're going to have. So then from those 22 students, 14 of them gave that final Hershey's Kiss, I don't know why it says kiss, they had that final kiss the highest rating. That's interesting, because that's 14 out of 22. So that's it looks like what they're getting at is this, why is this so high? Now, since they had 5 different kisses to taste, if there was no preference, that means you had a 1 in 5 chance of picking any one, right? So then the probability that they would pick the last kiss is 20%, or 1/5. So let's keep this in our mind as we're solving this, because the idea is to be like, well, if there is no like special like power in and eating in the last kiss or the last thing you're tasting to be for you to be biased, like it doesn't cause like some psychological bias, then the chance of you picking it will be 20%. So is it rare that 14 out of 22 of them would pick that last one? Like, is that rare? So when we say rare, I know like in real life you don't think like of calculations, but if you flip the coin like 100 times and you got 100 heads, you'd probably be surprised, because like whoa, that's how do you do that? You may not know the calculation in your head, but it's probably virtually zero. It's 1/2 to the 100th power, which is virtually zero. So intuitively, you know that things that have a very low chance of happening, you're going to be surprised by. You're going to think that there's something else going on. So if I flip the coin, let's say 100 times, and I guessed the right heads or tails, or let's say I flipped the coin 100 times and I got 100 heads, you'd be like, something else is going on. This guy's got some powers. It's not just due to chance. So you would run a calculation. So that's the whole idea here. But first, let's do a practice calculation. So let's say, what is the probability that exactly 5 of the 22 would prefer the last kiss they tried? The 5 of the 22. So going back to that formula here, we're just going to have the probability that x equals 5. We're going to use binomial PDF. So let's make sure we define what we're dealing with. So we have a binomial distribution, or binomial random distribution, where x will be the number of participants that preferred the last kiss that they tried. And we have 22 trials, so n is 22. The probability is 0.2, so p is 0.2. And the number of successes is 5, because we're saying exactly 5. So again, we're going to use that binomial function to find the probability that x equals 5. Here's how it would be when we were doing it earlier. We would do this, we would do n, choose k times p to the k times 1 minus p to the n minus k, and do this by hand. It's fun and all, but now that we have this formula, we can go ahead and run it quickly and use the binomial PDF function in our calculator to do it. So here's what you would get by doing it by hand. But let's see if I do it with the calculator. So I'm going to go to distribution, go down to binomial PDF, n, so 22, comma, p, 0.2, comma, k, which is 5, so npk, so the binomial PDF, bang, I get that answer, 0.1897, so about 19%. So about the same as if it were to do by hand, but that's faster. So again, make sure you write out what this means. So this is saying that the probability that exactly 5 of the participants would pick the last kiss that they tried will be about 18.97%. All right, now let's do the part B. What's the probability that 14 or more of the participants, so 14 or more of the 22, would prefer the last kiss that they tried? So let's think about this. If we're talking about the probability that 14 or more of them would prefer the last kiss that they tried, 14 would be in there, 15, 16, 17, 18, 19, 20, 21, 22. All those values will be in there. All those values will be in there. So, mathematically, we have a binomial distribution where n is going to be 22, but k is going to be 14. P will still be 0.2. So we're trying to find the probability that x is greater than or equal to 14. Still, again, npk. And since we're saying greater than or equal to 14, this will be equal to the probability that x is 14 plus the probability that x is 15 plus the probability that x is 16, all the way to x is 22. So this is the equivalent to that. Take a second to absorb that, make sense of that. Now, this is going to be tedious to calculate. You can do it by hand, you can do it by your calculator, but having to calculate each of these and then adding them is going to take you some time. It may take even close to an hour. Like, it's going to take a lot of time, and you don't want to have to worry about making a little, careless, silly mistake. But first, understand this, because if you understand this, going back to just the idea of probability of the basic probabilities rules, we're going to use the complement rule to figure out that the probability that x is greater than or equal to 14, that'll be the complement of x being less than or equal to 14. So the probability that x is greater than or equal to 14 will be equal to 1 minus the probability that x is less than or equal to 13. So again, absorb this, because one, remember, the only way you can get, so all the possibilities would be that x would be 14, 15, 16, 17, 18, all the way to 22, or it could be 1, 2, 3, 4, 5, 6, all the way to 13. So remember, in probability, all the possibilities have to add up to 1. So again, in this case, the probability that x is greater than or equal to 14 will be 1 minus the probability that x is less than or equal to 13. And you're going to end up getting it nearly like 100%. Now you're like, before I'm gonna go over how I got that in just a second, but you're probably thinking like, why do you do it that way? Why don't you just figure it out this way? Well, the only downside about this is that, well, the downside about the calculator is that the calculator function only finds the probability that x is less than or equal to some value. So we're trying to find greater than or equal to 14, but we can't do it with this function because we can only do less than or equal to 14. But you can use this to help you to basically figure it out by just subtracting it from 1. So that's what I did here. So I find what the probability that x is equal to, I find the probability that x is less than or equal to 13. So I go to distribution, but this will calculate the power up. I go to binomial CDF, cumulative density function, and memorize the syntax, NPK, but this time it's less than or equal to k. So n is still 22, so 22 comma p, n 0.2, and then k, which will be 13. And I get 0.99999, which is right there. So 1 minus this, so 1 minus 0.9999, which will, you can probably already tell it's going to be like virtually 0. So the probability that x is greater than or equal to 14 is going to be nearly 0. Nearly 0. It's a super small probability. Now let's think about what this means in the context. Remember, this is actually a real experiment done. Like, is this like something rare? Like, and if you're going to study psychology, or I'm always interested in like these types of studies. But if you're wondering like, is there something to, being biased towards the last thing that you taste or eat? Because 14 out of 22 picked it. And that if there was if there was nothing else at play, if it was simply due to chance, we're saying that the odds of this happening is nearly 0%. Is nearly 0%. Again, if it's like if I flip a coin and I get 100 heads in a row, if the coin was fair, the chance of that happening is like virtually 0. And you're probably gonna be like, what the heck's going on? This guy has some magic powers. Technically it's possible, but the chances are so low. So then we would probably think that there's something else going on. But that's what you want to keep in mind. So there is essentially a 0% chance of 14 or more of them for the last case that they tried, if it was just due to luck. So keep that in mind, because we're going to do some more of these in the next lesson.